Hi everyone, thank you for joining. So in this video we're going to investigate one of the well-known equations in physics. E is equal to mc squared, namely Einstein's energy-mass relation, right? And we will look at a thought experiment that Einstein himself invented in 1906. So to be able to do this experiment, this thought experiment, that we need to know one more thing, that is, if you recall de Broglie's wavelength, we have momentum is equal to h over lambda, and we also have for a photon that lambda is equal to c over f, right? Speed over frequency. If you simply combine these two equations, we have p is equal to h over c over f. That implies pc is equal to hf. And if you remember photoelectric effect, right, we have energy is hf, which is equal to pc. In other words, the momentum is equal to energy over c, right? So let's put this formula in a box, right? We have energy is equal to pc. Okay, now what we have in this thought experiment is that we have a box whose mass is m and the length is l, right? So what's happening here is that the radiant energy, in other words, the burst of photons are traveling from the left-hand side of the box to the right-hand side, and the second picture, it simply hits the wall of the box. But of course, this will create some recoiling effect, just like if you were shooting a gun will push back, right? So same recoil effect takes place here. The total mass of the photons, as I've indicated here, is little m. So the momentum of the box, well, it's simply the mass, which is m minus m, times the velocity of the box. Yeah. Notice that we are saying m minus m because we're subtracting the mass, the little m, the mass of photons, right? And we have momentum is equal to energy over c. That implies we have m minus little m times v is equal to e over c. That implies the velocity of the box is equal to energy divided by m minus m times c. Okay, so this is the velocity of the box, right? Now, the time that photons take, so let me write it explicitly, let's call t, is the time that the photons take is equal to L minus delta x over c. If you look at here, because of the recoiling effect, the distance traveled is L minus delta x, and that's divided by the speed of the photons, which is c, right? So that means we have delta x is equal to vt, that's equal to e over m minus m, c times L minus delta x over c, or we could write it as e into L minus delta x divided by m minus m c squared. Now, if we rearrange that, in other words, combining that with that, we will have m minus m c squared delta x is equal to e L minus e delta x. If you make delta x the subject, so delta x into m minus m c squared plus e is equal to el. So that implies delta x is equal to el divided by m minus little m c squared plus e. So the most crucial assumption to make here, now center of mass doesn't move, right? So that's an important assumption we're making. Why is that? Well, if you think about it, the photons are initially on the left, right? But then the same photons, same mass is on the right. So, and also we're taking the mass of the photons to be, of course, if you think about it, it will be very small, almost insignificant. So we will treat the center of mass as if it doesn't move. Okay, so let's take this to be origin initially. So initially we have photons here, right? And then we have the center of mass here, which is at L over 2, because the length is L. and the mass is m minus m. In other words, m minus m at position L over 2 initially. Yeah, this is initially. And the photons are at the origin O. So initial position, center of mass, I'm going to call I for initial. So we have mx bar is equal to m times 0, photons are at the origin, plus m minus m times distance, which is L over 2. Well, that implies x bar is equal to m minus m over L over 2m. Now, if you look at the final picture, in other words, when the photons reach on the other side, okay? So what we have here now, the photons are here on the other side of the box, and the box has recoiled by delta x, so the remaining distance is L minus delta x. So if we do position, center of mass, I'm going to call it F as a final, well, that would be, if you simply think about taking the moment, so we're going to have m minus m to L over 2 minus delta x plus m L minus delta x, right? Okay, but we assumed that the center of mass doesn't change, so that means that must equal to mx bar initial. So in other words, we have m minus m into L over 2 minus delta x plus m L minus delta x must equal to m minus m over L over 2, okay? So if we start cancelling now, what are we going to have? Well, we will have m minus m to L over 2 minus m minus m delta x plus m L minus little m is equal to m minus m L over 2. So let's get rid of that and that. That means, and let's expand the rest. So we have minus m delta x plus m delta x plus ml minus m delta x. So that goes with that. That's equal to 0. So we have ml minus capital M delta x is equal to 0. In other words, we have ml is equal to m delta x. But what is delta x? Well, delta x is from here. This is what delta x is, right? So let's plug that in. So we will have m times e L over m minus m c squared plus e. Okay, and let's combine this with that. So we're going to have, we have ml into m minus m c squared plus e is equal to mel. Now let's get rid of L. We have m into m minus m c squared plus em is equal to me. Now let's take this on the other side. That will give us em minus m, so that's equal to m minus m c squared, right? So let's get rid of that, and we have the well-known famous formula now, mc squared is equal to E, right? Okay, well, I hope you found it interesting. I hope you found it inspiring. So this is Einstein's famous energy-mass relation. Thank you very much for joining, and I look forward to seeing you in my future videos. Thank you.